I'm rolling.
Alrighty. Yeah. Welcome to math class. Today is basically focusing on division, but I wanted to first do a little bit of review and add in a few extra cool stuff. So first, if you recall, we started out with numbers, counting. The number 2 means you can map these two things to these two things. That's where we kind of start out with what the notion of number is. And then we had the digits, 0 through 9. And then, very importantly, after 9, we have 10. And this 10 meant, we kind of had this new unit of a 10. And then we start over at 0 here. We go through those numbers up to 19, and then we increment the 10 to 2, and so on. And then we had the hundredths and thousands. And so, kind of very importantly, 523 means you have 5 100 bundles plus 2 10 bundles plus 3. Or you could also write that as 5 times 100 plus 2 times 10 plus 3. So that's what the number means, right? And it's going to be very important for division to keep that in mind as to what we're actually talking about here. Alrighty. And then, let's see. I taught you the technique of doing mathematics from left to right. So, for example, 237 plus 426. Start on the left and add down. So you have 6, and then a 5, and then a 7 plus a 6. That's going to be greater than 10. So the idea was to kind of like take 3 from the 6 to get a 10, underscore this 5 to indicate that extra 10, and then you're left over with a 3. And so the total is 663. So that was the basic addition strategy. One thing I didn't tell you about, and I'm telling you now, is the idea of seeing whether this is correct by doing something a little bit crazy looking. And this will actually link into division, which I'll explain next week. But basically, the idea is add the digits and then do the operations. And so, and that should be the same as doing the operations and then adding the digits. So for this example, 2 plus 3 is 5. 5 plus 7 is 12. So doing checking this, well, summing the digits. You get 12, but I actually want a single digit. So I do 1 plus 2 is 3. So this is 2 plus 3 plus 7, and then this is 1 plus 2. And down here, 426. Well, 4 plus 2 is 6. 6 plus 6 is 12. And then we get 3. And now I add up these 3's and I get a 6. Good. Now over here, I add those digits. 6 plus 6 is 12. 12 plus 3 is 15. And 15, 1 plus 5 is 6. So that's how you can check that you've done this most likely correctly. Most mistakes you make, this will catch. It won't catch all of them. There's another technique that if you do both of them, we'll catch them both. And the actual technique, there's a little bit more black magic involved, but we'll just start with here, adding the digits. It works for the other operations, understood properly. So let's see. Let's remember how to do subtraction. Now, subtraction, when we line it up, the larger number has to be on top. If you're subtracting the larger number from the smaller number, then the result is negative, but you still put the larger number on top and subtract. Again, left to right, 4 minus 2 is 2. 2 minus 3, well, we don't want a negative number here. So instead of like subtracting 3, we look at its complement, meaning the number that adds to 10. So you replace kind of like this minus 3 with a 7. And then 7 plus 2 is 9. And you've kind of carried a 10. So you slash that to kind of remind yourself that you've done that, so you've lost 1 here. And so this is kind of, so if you kind of think of this as like a minus, kind of think of that as a minus 3, replace that with plus 7, and that's how I get the 9. 6 minus 7, and it's going to be negative, so replace the minus 7 with a plus 3. Plus 3 and 6 is 9, but had to cross that out. And so you drop those, and that's the answer, 189. Now, to check whether this is right, you can do the checksums, but and you can do it by subtracting, but what subtraction also means is that what the claim is 189 plus 237 is supposed to equal 426. So that's, what we need to be true. And so if we sum the digits here, 9 plus 9, 18 is a 9, and plus 7 is 12, that's a 3. 3 plus 9 is 12, and 12 becomes a 3. Over here, 4 plus 2 is 6, 6 plus 6 is 12, 1 plus 2 is 3. So that gives me great confidence that I've done that correctly. So you can also just do the addition. Most likely, if you made a mistake doing subtraction, when you do the addition, you won't make the same mistake. So if you got the correct, what you're starting out, be correct. But this is, quicker. Anyway, so that's addition and subtraction. Again, left to right, left to right. And we use this underscore to say add 1, and the slash to say subtract 1. Yeah, so this method would fail if so it's doing division by 9 and having a remainder. That's what these numbers are. And so if you're off in such a way that doesn't change the remainder, then it will not catch that mistake.
All right, you're good to start.
Okay, good. Alrighty, so that was addition and subtraction. And now a bit more pertinence to what I'll be mostly covering is a multiplication review. So, I don't know, let's say 252 times 37. So we again start on the left. That means starting with the 3 and the 2 here. And so let's see. And okay. There's a couple things. One, how many digits are in the answer? Declan?
5.
Yes. So we add that up and we get 5. Now, it could be less, right? One less, basically. So it's sort of 5 digits, maybe leading 0. So, and just sort of to always kind of think about it, when you're doing multiplication with these digits, always think in terms of 2 digits. So 3 times 2, it's probably good to think of it as 0.6. Now, when I introduced this, I did this technique where, so I had 3 times 2 is 6, and then 3 times 15, that leading 1 will go underneath that 6, and then you have a 5. Then you have 3 times 2 again, so that's a 0 and a 6. And that's kind of this top level. So basically 7, 5, and 6. And then, so roughly speaking, at this point, I could say it's 7,560, kind of a ballpark estimate there. So maybe around 8,000, because I'm going to add some more. Who knows? All right, now we do 7 times 2. It's shifted over by 1, and so we get 14 here. And then this 3 and a 5 from the 7 times 5 is 35. 7 times 2 is 1 and 4. And then I add them from left to right. 8, 9 plus a 3, so that's going past 10, leaving me at 2. When I add the 1 from 3 to the 9 to get the 10, I have 2 left over. 6, 5, and 6 and 5. 11, 12, and we got a 4. So, and the underscores were adding. Okay. So that's how we do it. Now, as leading up to doing division quickly, what I'd actually recommend is getting used to doing part of this in your head. So 3 times 2, the left digit is 0. Put that down. 3 times 2, the right digit is 6. Keep the 6 in your mind. 3 times 5, 15. Left digit is 1. So that was 6 and a 1. So you just write down 7. 3 times 15, the right digit is 5. 3 times 2, 6. The right digit is 0. So that's a 5. And then the right digit here was 6. Should come out to be the same thing as over here. And then 7 times 2, left digit is 1. 7 times, and the right digit is 4. Keep that in mind. 7 times 5, 35. 4 plus 3 is 7. Then right digit is 5. 7 times 2, 14 again. 5 and 1 is 6. And then right digit is 4. So hopefully that all came out the same. 2, 1, 2, and 4. So less writing, and it doesn't matter that much in multiplication in the sense that it's not that much more clutter, and it's a little more mechanical to do it this way. But when dividing, we do multiplication as part of a step, and so the less you have to write when doing that, the better. All right, checksums work for multiplication as well. So 252, add them up, 2, 5, 2, that's going to be a 9. 37, add them up, you get 10, add that up, you get 1. And then, so 9 times 1 is 9. So that's cool. And then, oops, where was the actual? The actual answer to the multiplication was 9, 3, 2, 4. This adds up to 18, I believe, and that becomes 9. 9 equals 9. So again, you can check it by adding up the digits and then doing the operation, and that should be the same as doing the operation and adding the digits. Okay. So it's a quick review of left to right arithmetic. Any questions? Okay. Alrighty. Now, one thing that's very important about multiplication. Well, let's see. First things, what did multiplication represent? It represented basically like, 5 times 3 represents 5 plus 5 plus 5, or 3 plus 3 plus 3 plus 3 plus 3, right? They're all 15. The wonders of mathematics, these two things are the same. It's true for all. Whenever you want to multiply, you can think of it as adding one of them the certain number of times as the other number. Now, one property that's pretty important is the distributive property. Neither algebra nor division would get very far without this property. And it basically means that, you can do the multiplication first. I guess do the sum first and then do the multiplication, or multiply each of them terms and add them. So, right, and 5 times 7 is 35. Here it's 14 plus 21, or 35. So that's the crucial property. When you got a sum being multiplied by something, you can distribute it. Just like that. Okay. Alrighty. 25. Okay. So. Now on to division. Well, first, what's the relationship of subtraction to addition? Yeah, they're opposites. They undo kind of each other. And in the same fashion, division undoes multiplication. So, division undoes multiplication. All right, so if I took 5 times 8, and then I divide it by 8, then that would be 5. This means divide by. Also would write 8 divided by 40, like this. Put it up like that. And there's also, so I should write 40 over 8. 40, and then the division symbol. I think I've only ever seen that in the context of K-12 math. Rarely does anyone write the symbol, but if you see the symbol, that's what it means. It means to divide this number by that. And this is another symbol, and that's another symbol. So those are the symbolic things, and fundamentally it means you're viewing the one thing as a product, and you're trying to get rid of the, seeing how many times you need to multiply 8 by to get 40. How many, well, let's see, I don't think that's quite right. How many, what do you multiply by? what do you multiply 8 by to get 40? Or kind of in a symbolic fashion, you could write that as 8 times x equals 40. So these are all asking for an answer of 5. 5 is the answer. Now, the best way of getting good division is to know your multiplications of single digits and be able to undo them. So it's knowing that 40 is 5 times 8. And so if you divide by 8, you get 5. But if you're really stuck, what you can do is, just like multiplication is repeated addition, division is repeated subtraction. But there's a twist on this one in that, so you take 40, and if you're dividing by 8, you subtract 8, you get 32. Subtract 8, you get 24. Subtract 8, you get 16. Subtract 8, you get 8. Subtract 8, you get 0. How many subtractions did I do? 1, 2, 3, 4, 5. 5 subtractions. So that's what division is also doing. It's saying keep subtracting the number you're dividing by until you get 0, or you get something less than the number you're dividing by, basically. All right. Mentally, what we're doing, you can view it in a couple of different ways. So let's say I've got $40, and I want to split that money up to 5 people. Then, the division problem would say give each of those people $8, right? So that's one view. The other view is, I always have such a problem with flipping this. Equal to the, yeah. So the other view is I want to give $8 out. I've got $40. How many people can I give $8 to? Right. Those are two distinct questions, and that's sort of how you do it. All right. There's also yet another way. So if you can recall, probably bad to have done this many. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Hopefully that's 8. 8 columns and 5 rows. You count the number of squares, and it should be 40 squares. So that's 8 times 5. So another way of viewing division is you've got your 4, 5, 6, hopefully 8. 8 columns, and then you want 40 boxes. So how many rows? Okay. So all different ways of viewing division, also different ways of exploring division. Not just a simple magic trick of undoing multiplication. You can get your hands dirty. Like, for example, with this, you say, okay, I put in one row, I get 16 boxes. That's not enough. I put in another row, I get 24, 32, 40. And, there you go. All righty. Any questions about kind of what division is supposed to be doing? Then let's try some examples. So, let's say, 12 divided by 4. So, Amber?
3.
So we write 3, and that means 4 times 3 equals 12. So, you know, you just should kind of remember the multiplication stuff and be able to kind of reverse it. These are kind of the fundamental facts, the single digits into these doubles. Now, what about 4 into 13? So I've got $13. I've got 4 people. I'm giving $1 to each person. How many dollars do I give out? 3. Yep. What's kind of the hesitancy? There's something weird about this, right, Declan?
There's an extra one, a remainder.
Right. So 4 divided by 3, you'd say 3, and then we might write remainder 1. Generally, we'll use fractions. That's a little bit later. And what does it really mean? It means this is the mathematical fact. 4 times 3 plus 1 equals 13. Right? So that's the mathematics of what we're doing. 4 times 3 plus 1 equals 13. So you have and we say it in different ways, but this is the fundamental thing to keep in mind when you've got kind of a leftover. Now, let's say I did that wrong. Let's say that I did 4 into 13, and I thought it was 2. So I write 4 times, well, one thing, the reason why we kind of write this stuff this way is because we'll do 2 times 4, and we'll write 8. So this is 4 times 2, and I have 5 left over. Now, 5 is bigger than 4, right? So I've still got $5, which means I can give another round of $4 out. And so, need to continue. 5 is bigger than 4. So I was wrong about that. And so I just put, notationally, if I get that in that state, I can put a dash on top. I put it below, except the way we write it, we've got the thing there, so I put it on top. And that means I do another subtraction of 4. Remember, division is repeated subtraction. I have 1 left over, and so that's the result. So the answer is 3 remainder 1. So even if you kind of guess low, you can fix it up without having to start over from the beginning. Alrighty. Now, there is a question as to what to do with the remainder. I will mention that shortly. But let's just try another couple of problems. 7 to, well, let me write things in slightly different ways. 35 divided by 7. What is that? So, David?
Is it 5?
It is 5. And as I said, you can subtract 7 repeatedly. You can know your multiplication tables, or you can just start adding up 7. 7, 14, 21, 28, 35, it's 5. All right. Okay. Let's see. All right. Now, as I said before, this fact is also the same as basically this fact. They're kind of asserting the same thing. 35 divided by 7 being 5 is the same as 7 times 5 being 35. So when division is clean, like this, nothing left over, then these are factors of the number. So factors are basically anything that divides cleanly into the number, or that you can multiply by some other number to get that number. So are there any other factors of 35? Is there anything else we could divide by and get clean division with? Could I divide 35 by 8 and get something nice? For example, no. What can we cleanly divide 8 into that's less than 35? Well, if you think about 8, 8, 16, 24, 32. The next one's going to be 40. So 32, and that's a 4. So that's going to be 4, and then a remainder of 3. So 8 is not a factor. Now, there are sort of 2 trivial divisions you can always do into a number. Like you can always divide into a number and get something nice out of it. It's trivial. So you can't see it. What? No. So 35 can be divided by 7, can be divided by 5 cleanly. There are 2 other numbers I can divide 35 by, but they're kind of pointless. Josh?
35.
Yep. So 35 divided by 1 equals 35. And 35 divided by 35 equals 1. So 1, 7, 5, and 35 are all the factors of 35. And 7 and 5, they're called the proper factors, meaning that there's actually a point to doing the division, unlike 1 and 35, which there's no point. Now, let's look at the number 7. 7, can I divide this up nicely and not trivially? So is there something I can multiply by 2 things, not 1 or 7, that give me 7? No. So like 7 divided by 2, not nice, meaning, well, it's like 3 and remainder 1. 7 divided by 3, not nice. That's 2, and remainder 1. And I'm going to skip over 5. 7 divided by 5, not nice. 1 and remainder 2. So the reason I chose these and chose 7 is that these are the primes, prime numbers. Nothing divides into them. Except 1 and themselves. So if I want a clean division and have a prime, I'll be sad. All right, so primes, factors, all that good stuff. Now, let's try something that's the opposite of a prime, something with a couple of different factors. So, factors of 12. All right. Well, does 2 divide into 12? Yes. So we've got 2. And when you divide 12 into 2, what do you get?
6.
Mm-hmm. Okay. Does 3 divide into 12? What do you get? 4. We also have 1 and 12. Does 5 divide into 12? No. I already got 6. And after that, they just really can't, right? You're just like, for example, 12 minus 7 is going to be 5. And you don't get anything kind of clean until you get to the 12. Alrighty. So it's good to kind of get a little comfortability with factors. We'll see with fractions, it's useful to kind of be observant of what kind of things divide into it. So what divides into these numbers? It's like after kind of doing the multiplication tables of the single digits and seeing how they reverse, and then factors are kind of the next step to keep in mind with those simple 2-digit numbers. All right. Now, today I will only do dividing by single-digit numbers with some long division stuff. So it might actually be called short division. Next time I'll do the long division with a longer divisor. It's kind of the same principle, but here we have it. Let's see. So first, 7 divided into 441. So what does this mean? Well, basically, we want to find a number such that when you multiply it, right, you get 441. Now, actually, before I get to that one, maybe I'll do something slightly simpler. 7 into 77. So, what does this mean? So, we want to, well, let's build it up. 7 into 70. Seventy is 7 times 10, right? So 7 into 70 would be 10 because of this. So the way we kind of think about this is we say, okay, we got the 7, and we try to divide it into this leading digit. 7 goes into this 7 once, so I put a 1 up here. It's over the tens place. It's kind of a 10 thing. And then, so this means basically that we have 10 sevens in this number. So I can say 10 times 7 is 70. And I subtract it, and I have 0. And so, in this case, I'm done. What did I do? This is a shorthand for saying I can subtract 7 from 70 10 times. That's why I'm subtracting here. I'm saying, okay, I'm going to multiply this thing and get 70. Now, when doing 7 into 77, I take that 7 and I say, okay, I have 70. Ignore the 7 for a moment, and I write a 1. And again, this is in the tens place, so I do 1 times 7, and it's the tens. And so I subtract, and I have 7. And then I have, how many times does 7 go into 7? Once. And so subtract 7, and I get 0. So 7 times 11 is 77. That's the claim. All right. How about 7 into 84? 12. So one way to, of course, see it is that I added 7, and so I added another thing, and you got that. But doing it this method, 7 into 8, 7 divides into 8 one time. 1 times 7. Subtract a 7 here. If you like, you can put a 0 here still. And you get minus 70. 14, 7 into 14 is 2. So we first try to divide the digit into the leading number, and then we bring it down, multiply, and so forth. Now, what about 7 into 14? So does 7 divide into 1? No. So you have a 0. And then, so nothing's changed, so now you got to do the 7 to the 14, and you get 2. Now, there's no real need to write the 0 here, as long as you remember to put the 2 over the appropriate place. All right. Let's say 7 into 79. Is that going to come out cleanly? No. 7 into 7, 1. I don't really need to put a 0 there, so I won't. I get a 0 here, though. And I get a 9. 7 into 9, 1. Subtract 7, 2. 11, remainder 2. All right. And again, this means 7 times 11 plus 2 equals 79. All right. Do you remember the checksums from earlier? Well, does this work? Do they work with division? Yes and no. You can't do the operation of division with the numbers, but remember that division is making a claim about multiplication, and we can apply the checksum to the multiplication. So here, for example, you get sum of digits is 7 here, and the sum of digits is kind of a 2. 2 times 7, 14, and that's a 5. Here, add the digits, 14 and 5. And so, you can do it that way. And it's nice because with remainders, you can do that too. So you get a 7 and a 2 for the checksums. 7 times 2, 14. Add up on your 2 here, 16 and 7. And here, 16 and 7. So you can check your division facts, and you want to do that with division because it's messy. But you just kind of write out what you mean in terms of multiplication and addition, and then you can do that, the checking of the answers. All right. Now, all of those problems are things that, there isn't much need to write down too much. So now let's go try 7 into 441. So, does 7 go into 4? No. Does 7 go into 44? So what's the closest thing that's a multiple of 7 that's less than 42? All right. Ah! Less than 44. All right, well, it's 42. And 7 divides into 42 6 times. 6 times 7 is, of course, 42. And you get, so you subtract this. And remember, so this is kind of like, you can think of that 6 sitting there. It's above the tens place, so you think of it as 60. 60 times 7 is 420. So you can kind of think of a 0 going there. And then you subtract the 2. You get 7, you get 21 left over. 7 goes into 21 3 times. And you're good. All right, so that's the standard division. With a single digit, it's not horrible. And if you notice, so this is actually conventional. Left to right, people. They got one right. 1 out of 4 ain't bad. You do it left to right with division. Nobody ever does it right to left, so that's a blessing. Now, you can also do some of this mentally, which is kind of nice. You still kind of start the same way, but 7 times 6, 42. The left digit is 4. You're going to subtract from here. You get a 0. The right digit of 42 is 2. You subtract that from 4, and then you just get 2. And then you've just got your 21 right here. And so you don't actually have to write down all those things. You put a little bit of effort in your mind, and then you're good. 7 to 21 is 3. 3 times 7, left digit is 2. 2 minus 2 is 0. And 3 times 7, right digit is 1. 1 minus 1 is 0. You're good. So you don't have to write everything out in long division if you don't want to. Let's try another one. 8 into 5,936. Yeah. I'm not doing random division problems because I want things to be kind of mostly nice. So there are still some tricks. But 8 into 59. So 8 into 5, no go. 8 into 59. Well, what's the thing closest that's divisible by 8 to 59? 56. 8, 16, yada yada, 56. That's a 7. And then 7 times 8 is 56. You do your subtraction. You get 336. 8 goes into 3. No. 8 goes into 33. Yes. Goes into it 4 times. So you have 320. Then you bring down the 16. Do the subtraction. 16. 8 into 16 is 2. Just to be sure. All right. And the shortcut version, again, it's not much of an insight rather other than just putting it in your head, but 8 into 7, 8 times 7, you got the 5 on the left, that's 5 minus 5 is 0, so you're good. And then you have a 6, 9 minus 6 is 3, so there's your 336. And then 4 into 33, 8 into 33 is 4. And then you do the subtraction in your head again. Left digit is 3, and then you got 2, and you get a 1, and then 1 and 6, and then you get a 2. So you can use this to kind of write down a few notes in between, but you know, it's essentially the same content, but a lot less writing, right? But the price is putting it more in your head. All right. Okay. Try one more. All right, 8 into 54. Anybody? Okay, well, 48 is the closest one, and that's a 6. So 6 times 8, you get 48. That's going to be 624. 8 into 62. 7, 560 if you like. You do that subtraction. Let's see, whatever that is. 64, and then you get an 8. Right. Now, if you do it the shortcut way, a little bit something interesting happens. So again, start the same way. So 6 times 8, 48. So you have a 4 on the left. 5 minus 4 is 1. And then you do, you have the 8 from the 48, and you're subtracting that from 4. So 4 minus 8, that's going to be negative, so you do the carry thing from subtraction. So you replace the 8 with a plus 2, cross that out, and you have a 6. And so now you have 62. Same as there. 8 into the 62 we had was 7. 7 times 8, 56. So again, 5 from the 6 is going to be a 1. And then you've got a 6, 2 minus 6. Place the minus 6 for the 4 and cross out. So you have a 6. And then 64, and you have 8. And that works. Okay. So that's sort of the short division aspect. With a single digit, it doesn't look that much better given a little bit of the mental strain, but when you get multiple digits in the divisor, it makes it a joy. Over the winter break, I was just computing 10-digit divisors. It was so glorious. All right. And as I said, you can check your work. So what is this? This is saying 678 times 8 equals 5,424. So you can sum up the digits. 13, 8 is 21, and that's a 3. And then you get the 8. 8 times 3 is 24. Sum up those digits, you get a 6. Over here, sum these digits up. 9, 11, 15, and 6. You're golden. Okay. Now, I do these things. We already talked about remainders. Now let's start talking about some of the other interesting things. Fractions. So, what's a fraction? Well, if I try to divide 2 by 3, or all these things, but fractions, we write it like this. It kind of means this. There's not much to say, right? In some sense, if like in terms of remainders and how many times it goes into it, because it's, so if you do 3 into 2, well, that's 0, and remainder, I guess 2, right? Haven't gone anywhere with it. So one can just shrug one's shoulders and leave it at that, but that's not very useful. So to make sense out of what this means, you can think of this as kind of a, sort of 1 unit, if you will. And then 2/3 means divide this thing up into 3. And that's sort of what 2/3 means. So that's the thing. In your mind, you have something that's 1, and you're dividing it into thirds, and you're taking two of those things. Now, let's say 1/4. So again, this is sort of like we've got these 4 things, and 1/4 would be meaning that. Now, do we have experience with that, with money? So think of that as a dollar bill, $1, and you want to divide it into 4 equal parts. Declan? Quarters. Which is also what we would just call that, is a quarter. But basically, divide into 4. And that's quarters, right? And so you just get 1/4, 25 cents. Now the 25 cents, that's a whole different way of writing this out, right? So 1/4 is, it's like, so if I just said, here's a quarter, right? It's a whole new thing. It's just what it is. There isn't something necessarily deeper about it. It's like just it's a new unit. It's like going from inches to feet. It's, you're changing kind of that. But we also know it as sort of 25 cents. And so what unit is that? What's a cent? Josh?
1/100th of a dollar.
Right. So this is sort of saying 1/100th of a dollar. And basically the assertion is that 1/4 is the same as sort of 25 1/100 units. So you have these, like, if you break this thing up into 100 bits, lots of things, and then you were to overlay this 1/4, it would be 25 of those segments. So the thing about fractions is it's kind of introducing a whole new kind of object into our discussion. And what one does with that is you write fractions kind of in terms of other fractions for whatever your purpose is. And that's really what a lot of fraction stuff relates to. Now, how do we actually write 25 cents in terms of dollars?
0.25?
Yep. So 25 cents is the same as $0.25, right? That's so 25 100 bits of a dollar, we write that way. And in general, these decimals use 1 over it's powers of 10 to write out numbers. So if we had 523, kind of where it started, we think of that as 5 times 100 plus 2 times 10 plus 3. Now, if I were to write 5.23, what that literally means is I still got the 5, it's just a single unit digit, plus 2 times sort of 1/10, or 2/10. And then 3 times 1 over 100. Right? And if you think of 20 cents, 2 dimes, so this is kind of like a dime, 2 dimes. That's the same as sort of like 20 over 100. So that's sort of what decimals mean. And this means is I kind of have to explain how to do fraction addition, right? But in terms of the presentation, we are introducing these new units of these powers of 10. Instead of going upwards, we had 10, 100, 1,000, so forth, we go downwards, 1/10, 100th, 1,000th. They get smaller and smaller. Now, why did I stop with the 2/3 and change to 1/4? Josh?
Fear of unholy numbers. And repeating decimals.
Yes.
I assume the first primarily, the second secondarily.
Basically, 1/3 cannot be expressed nicely. Well, I think it's kind of nice. Nicely in terms of fractions of 10. So if you try to divide up $1, for example, into 3 parts, you can't do that equally, right? I can give 33 cents to 3 people, and I get almost there, right? And there's like 1 penny left over. And everybody hates pennies, so we just ignore it and we pretend it's fine. But mathematicians can't do that. And so you have 1 penny that you're trying to divide into thirds to make it more equal. And you can't do that. So basically kind of the decimal expression of 1/3 is, and let me just write it out in full. Somebody please stop me. It goes on forever, which means sort of whatever it means to be add fractions, it would mean like you take 3/10, and then you add in 3/100ths. So that's 33 cents, 33 pennies, if you will, already accounted for. And then you divide that, take 3/1000ths, add that in, and 3/10,000ths, and so on. And so all of a sudden, we're faced with numbers that we can't express in terms of powers of 10 finitely. But that's okay. Nobody cares about these smaller bits in terms of penny. Well, I guess some people care. Yes. And all right. All right. One other thing to know about that we're almost basically fine with at this point is percents. So if I say something like 23%, that's a percent sign. Well, percent means per 100, right? And so basically we have the percent sign means if I want to write in decimals, I shift the decimal point over 2. So 23% is the same as 0.23. That's all it literally means. But its use is a little bit more, which I have to do some groundwork to get to. But in terms of what that symbol actually means, it just means we did that because humans like that. I don't know. So there's lots of different ways of writing these things out. They're all kind of equal. Now, one thing with fractions is adding them. So if I take 1/4 plus 2/4, what would that mean? Remember? Yep, 3/4. So again, if I think of dividing something up into 4 pieces, you know, the idea of adding the fractions is I've got one area here, I've got 2 areas here. I put them together, I'm going to have 3 areas. Right? So that's what this means. Divided these things up into fourths, add them together, and that's what we get. What happens if I were to do 2/4 plus 3/4? How many total areas have been shaded?
In total, it would be 1.25, maybe?
Yeah, but more simply, you got five areas, right? And so we can write 5/4. And you know, that means I've got my little drawing here, and I'm going to need another one. So I filled up all 4 of one, and then I've got one more left over. So I can also write this as 1 1/4. Or going back to it being like 0.25 in terms of decimals, be like that. Now, we could also write it in terms of decimals and do addition. that way. So 2/4. So if you had 2/4, you have 50 cents. And if you have 3/4, you have 75 cents. Keep that. And to add it, you just add it like we've been doing. 5 and 7, well, that's 12. So you put a 2 here, and a 1 over here, and then you add up that one, and you get your 5. One reason why we like decimals is because you can add them up like that, real nice and easy. Now, let's say that I have 1/2 plus 1/4. So 1/4, I divided the 1 up into 4, and the 1/2, I've divided that into 2 pieces and shaded that in. So what do I get? Remember?
3/4.
Yes. How does that happen? So when I look at this, I don't see 3 out of these shaded areas, right? And so what does one need to do? And of course, part of the clue is that's 3/4, right? So this half, I need to divide into 4 pieces. And so, when you divide it up like that, this becomes 2/4. And now, 2/4 plus 1/4 is 3/4. Now, how do I compute that 2/4 from 1/2? Well, basically, the true answer is I'm going to multiply this thing by 1 in the form of 2 over 2 and multiply the top and the bottom. So that's sort of the mechanical method you would do is you realize what you need to make these things have the same number of divisions into the unit, and you multiply, you kind of scale it up. So 2/4, it's saying you've got half of this thing, and so that's why we do that, and you know that because 2 times 2 over there. God, I'm fading.
You said
Just-
multiplying by 1 is trivial, James. Why isn't it trivial now? Or is it?
Well, yeah, I haven't changed anything, so that's the point, right? Is that this is just 1. Just multiplying by 1. So I haven't actually changed anything, although I haven't actually explained multiplying fractions, so I cheated there. But a lot of cool tricks involve multiplying by 1, adding 0. Those are good things to keep in mind, and it's absolutely essential in scaling these things. And how about 1/2 and 1/3? So Can I just multiply 2 by something to get it to be 3? No. Remember? It is 5, 6. So basically, they're kind of incompatible divisions. They're not kind of subsumed in one of them. And so what we do is we divide up this thing into, this one into thirds, and this one into thirds, and then we divide this one up in half, and half, and half. And now we count how much of the shaded area there is. So it's 3/6 and 2/6. You add them, and you get 5/6. And mechanically, you just multiply these things by the other number. 2/2 for the 1/3, 3/3 there. 3/6 plus 2/6 equals 5/6. Alrighty. One thing to note, I haven't really gone into the fraction multiplication, but note that I'm multiplying the top and bottom kind of separately. Addition, I am not doing anything to the bottom, right, other than trying to make them the same. I don't add them, I don't do anything, it just goes along for the ride. I'm counting the number of parts. It's good to put it early on in your head that addition of fractions is much more difficult than multiplying fractions. And yeah, it's just not symmetric. Anyway, that's far more than enough for today. Any questions? Awesome. Next week I intend to do longer digit divisions and more into fractions and using more like percent problems and what one might see. This is really the beginning into algebra stuff.